We want to find the smallest positive whole numbers of n such that this expression here is entirely real. I'm going to make use of the De Moivre's theorem once again, replacing w by 2e to the power of minus I pi over 6 that I found in the previous part of the question. So this is going to be 2 to the power of n, e to the power of minus I n pi over 6. As for w conjugate, it should share the same modulus as w, so it is 2, and e to the power of the argument of w conjugate is going to be negative of the argument of w, so it is pi over 6. Let's try to combine this together. This 2 to the power n divided by 2 is 2 to the power of n minus 1. As for this, it is going to be e to the power of I of minus n pi over 6 minus away pi over 6. And this is 2 to the power of n minus 1, e to the power of minus I pi over 6 multiplied by n plus 1. In order for us to analyze the conditions such that this is purely real, I need to first re-express what I have here into the Cartesian form, because only then I can see the real portion of this and the imaginary portion of this. And what we want to do is to let the imaginary portion be equal to 0 to make the entire thing purely real. So let's try to convert this into its Cartesian form. It is going to be 2 to the power of n minus 1, then cosine of minus pi over 6 times n plus 1 plus I sine of minus pi over 6 times n plus 1. And if I were to multiply this in 2 to the power of n minus 1, cosine negative of an angle is the same as cosine of the angle, so it is going to be cosine of pi over 6 of n plus 1. And sine negative of an angle is negative sine of the angle, so it is going to be negative sine of pi over 6 n plus 1, and multiplying it by this, it is going to be minus I. It is going to be minus I of 2 to the power of n minus 1 and sine of pi over 6 n plus 1. And we want to make sure that w to the power of n over w conjugate, this entire thing here, is purely real. Which means that we need to let the imaginary part of this be equal to 0. So letting the imaginary part of w to the power of n over w conjugate be equal to 0, what we will have is a minus 2 to the power of n minus 1 sine of pi over 6 and n plus 1 is equal to 0. This is definitely going to be negative. If I were to divide this over, what I'm going to be left with is just this to be equal to 0. So sine of the angle pi over 6 and n plus 1, this is equal to 0. According to what we have discussed in our topical outline, when sine of an angle is equal to 0, there's actually a formula. Please take a look at that again if you cannot remember, because it is very useful for this kind of purely real and purely imaginary question. So sine of an angle is equal to 0, that means that angle must be equal to, according to what we have discussed, an integer multiplied by pi. So k here, I'm going to just write it as any integer. What we are supposed to do is, what if k changes? N is going to change. And we want to filter out all the positive whole numbers of n, and I'm going to select the smallest 3 of them. Making n the subject, n is going to be equal to 6k minus 1. And now I'm going to just sub different values of k in. For example, if k is equal to, let's say, minus 2, there can be a few different values of n. I'm just trying out a few different values of k. So if k, which is an integer value, if I were to let k be minus 2, is going to be minus 12 minus 1, so minus 13. If k is minus 1, then it will be minus 7. If k is 0, that means this is going to be just minus 1. If k were to be, let's say, 1, it will be 6 minus 1, it is 5. Now we get a first positive integer, a first positive whole number of n. If k is 2, 6 times 2 minus 1, it is 11. Or if k is 3, it will be 18 minus 1, it is going to be 17, and so on. Okay, and these are the three smallest positive whole numbers of n which the question is asking for.